Today I want to do the problems from chapter 2. So the first one we have is chapter 2, and it's question 5. And in question 5 it has some points along here. This is point 1, point 2, 3, 4, 5, and 6. And then there are a series of questions. A says, at time t equals 0, which way is the object moving? So this is a velocity versus time graph. So the velocity itself is graphed. So the value of the velocity is going to tell you which direction it's moving. So at time t equals 0, what we notice is that the velocity here, it's above the t-axis. So the velocity is positive. So it's moving to the right. B says, what about at point 4? If you notice at point 4, it's below the t-axis. So at 4, we know the velocity is negative, so it's moving to the left. Okay? C says, where does it reverse direction? So C says it reverses direction, and that's at 3 and 5. Because what do we notice? At 3, it's going from positive to negative, and at 5, it's going from negative to positive. So velocity goes from plus to minus, or from minus to plus. Another thing that's interesting is that 3 and 5 are both on the t-axis, so at both these locations, the velocity is 0. And if you want to switch directions, you have to stop and then switch directions. And D, what does D ask? It says, rank the value of the magnitude of the acceleration. So acceleration is a vector, so it has direction and a size. The size is the magnitude. And since this is a v versus t graph, the slope is the acceleration. Okay? And since we're dealing with the magnitude, we only care about how steep it is. So the steeper it is, the bigger the magnitude of the acceleration. So where is it the steepest? If I use a slopometer here, it's going to be the steepest at 2. It's going to be a little less steep at 3. No steepness at 4. 3 and 5 are the same because of symmetry, and 2 and 6 are the same, and 1 and 4. So the biggest acceleration would be at 2, and that's the same as 6. And then 3, which is the same as 5. And then 1, which is the same as 4, which is actually 0. So that's the first one. There's some more questions. All right, let's look at question 7. Let's look at question 7. So question 7 talks about 2 eggs, one that is thrown downward and one that is just dropped. I'm not going to draw all the ones out there, I'm just going to draw the ones that are relevant here. So if it's an egg and it's in free fall, if you're an egg in free fall, you're falling down with the acceleration due to gravity. So as you fall, you speed up. But if you're dropped, your initial velocity is 0. So I think for the dropped egg, it should look like that. So this is the egg that's dropped. Okay. What about the thrown egg? Well, if you're thrown downward, 2 things are important about you. One is that you have some initial velocity. That's an important idea. And the second thing that's important is if you have some initial velocity, you are still in free fall. The initial velocity does not affect your free fall acceleration. You will have a faster speed, but your acceleration is the same. So you start with a faster speed, but you're thrown downward, so it's negative. You're going to start here. And then you have the same acceleration, so this line and this line have to be parallel. So they're parallel because we know that the slope of the velocity graph is the acceleration. So parallel. Because the same acceleration, which is our free fall acceleration. So the moral of the story is the initial velocity does not affect the free fall acceleration. Okay. All right, let me reset for question 9. In question 9, we have 3 windows. I'll sketch them real fast. Here are 3 windows, and they're labeled 1, 2, and 3. Here's window 1, here's window 2, here's window 3. It talks about something, I think a tangerine or something, thrown upward past the windows. So the tangerine gets thrown upward past the windows. Okay? And then it wants us to rank, okay? It wants us to rank a couple things. So the first thing it says is rank the average speed of our tangerine, and we'll go the largest first. So where does it have the largest speed? Well, as it goes upward, what happens to it? It slows down. So where's it going to have the largest average speed? I think it's an easy one. I think it's 3, 2, 1. Okay? What about the time? Let's rank the time. Well, if it's slowing down, it's going to take less time to go across this one, a little bit more time to go across this one, and a little bit more time to go across this one. So I think the longest time in this case is 1, 2, 3. Ooh, what about the acceleration? Now you may be tempted to think that because it's slower, the acceleration is different, but it is not. The speed does not have any effect on the acceleration. These are all in free fall. Okay? Even though it's moving up, the acceleration is still down. So that means that 1 is equal to 2, which is equal to 3. Okay? These are all in free fall. Okay? They all have the acceleration of little baby g. Okay? And the last one, D says, what about the change in velocity? Which one has the largest change in velocity? Well, we're going to represent change in velocity by delta v. And one of the things that we know about acceleration, right, if we want to calculate acceleration, we can say that the acceleration, the idea of acceleration can be calculated if you know the change in velocity divided by the change in time. So if I rearrange this a little bit and get a conceptual framework through this mathematical representation that says the change in velocity would be the acceleration times the time. And so what does that mean? If I go back and I look at the time, it spends the most time across 1, middle time across 2, least amount of time across 3. And since they all have the acceleration, but the times are going to dictate the change in velocity. So the changes in velocity are going to be 1, 2, 3. And because it spends the most time going by this window, the change in velocity is the most. We know the change in velocity for an object in free fall here. The velocity changed by negative 10 meters per second for every second of time. So if it spends more time, more seconds here, it's going to have a larger change in velocity. Let me find the next question. So I got to draw the diagram. Question 11 wasn't assigned on your sheet, but I think it's going to be an important one. So what it does is it gives us a an acceleration versus time graph, and it says that there's an object that undergoes some different accelerations, and it wants to know which has the largest change in velocity. So I will sketch them out. Okay. I need more room here. All right, so these are 1, 2, and 3, I think. 1, 2, and 3. This is number 1, this is number 2, this is number 3. It says, which has largest? Now, I think in the text, I think it says change in speed. But here, because they're all positive, the change in speed and the change in velocity are the same thing. So the thing that we know, and the thing that's important, is that the area under the type of A versus T graph is the change in velocity. Okay, that's one of our rules. That's an important rule. Okay, and so now, because these are divided up really nicely, we can just count them up and see. So we're going to do it by boxes because the scale is the same. We got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, so I'll put 8 here. So here our delta V is equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. Delta V is equal to 8. And this one, 1, 2, 3, 4, 5, 6, 7. Delta V is equal to 7. So therefore, if I rank them, I have 1 is equal to 2 and then 3. All right, that is enough of the questions. All right, let's try to move. Let's try to move on to the problems. Give me 1 second. Okay, first one is problem 7. I'm not going to say it's a trick question, but it's a little bit of a tricky question. And so what we have here is we have 2 trains. They're moving at one another. All right, obviously they're not drawn to scale. We'll call this one train 1, we'll call this one train 2. And then in between them, there's a bird. I'll draw the bird like this. And we'll pretend that's a bird. It looks like an M. It's a seagull. It's flying this way. And the bird does something funny. He goes there, back, there, back, there, back, there, back. But by the time he gets to here, this train has already moved, so he might only get to here. And by the time he goes back, this train has moved, so he only might get to here, and then here, and then here, and then here. Right? So it wants to know how far does the bird fly. But it turns out this back and forth, back and forth, back and forth, it's a red herring. It doesn't matter for the story because we're going to use the relative velocity. We're going to use the relative velocity conceptual framework here. So one thing we know about relative velocity, so that says VREL. It's how fast are the trains moving at one another if one was stationary. Okay? And so in this case, we can do relative velocity, and it's usually velocity 2 minus velocity 1. That's going to be the relative velocity. So what do we know about this guy? So this guy's moving this way at 30 kilometers per hour. This guy's moving this way at 30 kilometers per hour. So what are their velocities? Because these are their speeds. Velocity you need to indicate the direction also. So this guy's moving to the right, that's positive. This guy's moving to the left, that's negative. So when I plug it in here, I have negative 30 meters per second, or kilometers per hour, minus 30. So the relative velocity is negative 60 kilometers per hour. And then the relative speed, okay, so it doesn't matter for the direction of the relative velocity at this point. We just want to know the speed. So we're going to see how fast they're approaching one another. So what this means is that they're both moving 30 at one another. So if this guy was at rest, it would be the same as this guy moving at 60 toward him. That's what that means. So one of the things we know is that our definition for speed is equal to the distance traveled divided by the time. That's something that we know anyway, right? This is like miles per hour or meters per second. This is how we understand speed as a concept in our everyday lives. So let's see how much time it's going to take for these two to collide. The relative speed is 60 kilometers per hour. The distance between them turns out to be 60 kilometers. That means, if we solve for time, time is going to be equal to 1 hour. So it's going to take 1 hour for them to collide. No big whoop. Classic problem. Let's talk about the bird. If I now talk about the bird, all right, they said that he hits a train and turns around instantaneously, so there's no speeding up or slowing down. The bird is going at a constant speed of 60 kilometers per hour. That's a bird's constant speed. Well, if we use our speed definition again, I know his speed is 60. I'm looking for the distance that he travels. I know the time was 1 hour until the trains crash. Therefore, he flies a total of 60 kilometers. And to me that's funny because, you know, your instinct is to go back and forth, how am I going to add those things up? Do I need to use some sort of infinite sum? And you could do that, we don't want to do that here. But it turns out to be pretty simple. He flies at 60 kilometers per hour for a total of 1 hour for a total of 60 kilometers. I know, it seems pretty cheap. Okay. So in problem 11, we're going to take a little road trip. You're driving to an interview or whatever. And it says that you're going to leave at 8 a.m. and you're going to arrive there at 11:15. So what's the total elapsed time for the whole trip? So it's going to be 3 hours and 15 minutes. So that's 3.25 hours. It's important to work in just hours because the units are like kilometers per hour, so we got to make sure all our units match up. Okay? So this is going to be an important idea later on. So let's talk about part one of the trip. In part one of the trip, it tells you that you travel at a speed of 100 kilometers per hour for a distance of 100 kilometers. Therefore, how much time does it take? Well, if you're going 100 kilometers per hour for 100 kilometers, it's going to take 1 hour. This is what the 100 kilometers per hour means. It means for every hour of time that travel, you go a distance of 100 kilometers. So that's just part one. What about part two? In part two, your speed, you have to slow down, so it's 40 kilometers per hour. The distance is 40 kilometers. Therefore, it took another 1 hour. Okay? No big deal. So then the question is, how much time do I have left? Well, I went an hour here and an hour here. So I had 3 1/4 hours. I've used 2 of them. Okay? So we need to figure out what's going on in part 3. Okay? We'll do part 3 up here. So I know that the distance speed, distance, and time. Okay? So this is the time here that it took. We know it went this far. It says, let me check the problem. I'm pretty sure it says that the total distance. The original total distance here is 300 kilometers. All right, so last part. How much do you have left? Well, the distance you have left is your original 300 minus the 100 for this trip, part of the trip, minus the 40 here. So you have 300, you subtract off 100 kilometers for the first part, 40 kilometers for the second part, and that leaves you with 160 kilometers. The time, we had a total of 323.25. We used 1 hour of it in the first part, 1 hour of it in the second part. That leaves me with 1.25 hours. And then this is where we're going to get the speed. I'll do it down here. Well, we know it's distance divided by the time. My distance is 160 kilometers. My time is 1.25 hours. And therefore, this is equal to 128 kilometers per hour. So that's the question. The question says, how fast would you have to drive to still get there? Well, we now know how much distance is left, how much time is left, and we divide, and we get 128 kilometers per hour.